Okay, so now we are continuing on with the titration of a weak acid and a weak base, and we are now at the equivalence point of this titration. And you recall, by definition, at the equivalence point, yep, and this time we're using millimoles. So the millimoles of the acid are equal to the millimoles of the strong base. So not much is different in this problem, except you have to figure out the volume here, because you'll know the number of millimoles based on your initial concentration. You've slept since this has happened, so let's start like we're at the beginning. So we have the neutralization step. We have the weak acid plus a strong base makes water and the anion. Okay, initially we started out in our problem with 50 mLs of 0.1 molar, which gives you 5 millimoles of the acid. At the equivalence point, we know we must have 5 millimoles of the strong base. And initially we have none of this and none of that. The change during neutralization is the complete stoichiometric 1-to-1 neutralization of all the H and all the OH. So this goes down by 5 millimoles. This goes up by 5 millimoles. And we subsequently make 5 millimoles of the CN ion.
Isn't it? What is the ion down?
Oh, thank you. Okay, so the water we're not concerned with. It's not going to affect the pH. Okay, so at neutralization, we have none of this left, we have none of this left, and we have produced 5 millimoles of the CN. Okay, that ends the neutralization portion of this, and we are going on to the Rice table. But we have one adjustment to make first, and that is you have millimoles here, you need molarity here, and you need the molarity of the only thing left, and that is the cyanate ion. So its molarity is equal to the number of millimoles divided by the total number of liquid. Now, do you know the total number of liquid solution?
Sorta.
Sorta, kinda. You know how much of the acid you added.
50?
How much base did you need to add in order to get 5 millimoles?
50.
Okay, how did you figure that out? Well, of the base, you know that you have 5 millimoles. Its molarity is 0.1, so the volume that you used, X, is equal to 50. So there you go. So your CN ion has a molarity of 0.05, what? 0.05 molar. It's over 100. 50.
Right.
Okay, now this is where it gets just a little bit different and a little bit confusing, and I'm calling on your expertise to figure this out. The only thing you have in the solution anymore is water and the conjugate base of a weak acid. What will happen here? Magic is not the correct answer.
Something cool.
Come on. What does that look? No, it hydrolyzes.
That's the word.
Hydrolyzing. Okay, so the conjugate base in water is now going to make
The acid and the OH.
very good.
It's not kind of like the bubble system because when you go to
Not at all. Completely different.
Okay, so let's now go into our Rice table now that we have figured out the equation that controls pH. So initially, we're going to have 0.05 molar CN. We're not going to really worry about this. We don't have any of this. The change towards equilibrium, some of this will form some of this and OH. At equilibrium, the equation that we could use to figure out our concentrations will be this. Now, you need to write the equilibrium expression that goes with this equation.
Don't we need
Isn't it
KB?
KB?
Thank
Yeah.
you. KB is equal to you're given Ka in your problem. That doesn't deter you because you can simply do this. I believe it's 6.2 times 10 to the negative 10.
You're correct. And
So
KB,
KB is going to be
1.61 times 10 to the negative 5.
correct. Okay, so 1.6 times 10 to the negative 5th is equal to x squared over 0.05. X, which is equal to the hydroxide ion concentration, is equal to
8.94
8.97 times 10 to the negative 4. From
How-
that, you
How'd you
can
get to
find-
7?
I don't know.
Alright.
It's equal to the negative log of this number.
That is the change.
Thank you.
You know what? This has been the sneeziest day. I think that, you know, we've been bombarded by pollen.
Yeah.
We have been
I'm certain we
bombarded by
want that to be on
pollen.
YouTube too. Okay. All right. So the POH is equal to 3.05. Therefore, the pH is equal to 10.95, and that is your answer. Now I want you to add a step D. Okay? Write this down on your paper. Step D. Find the pH.
Where should we write this at?
After 52 milliliters of NaOH has been added. Alrighty. Stop and think what has happened after 52 mLs of NaOH has been added. It's a basic solution. So we still have, starting out with our this time we have 5 millimoles. Now we have 0.1 molar times 52 ml is 5.2 millimoles. We have 5.2 millimoles of the OH, none of this and none of that. The change, this time the H limits, we'll use up all of this. And we'll make some of this. Alright, so neutralization, this is gone. We have 0.2 millimoles of this. And we have 5 millimoles of the conjugate base of the weak acid. Although the conjugate base of a weak acid is strong, it's not nearly as strong as the OH of a weak base. This trumps this every day of the week. Therefore, this is what controls the pH and not this. That means you can totally ignore this, any pH change that the conjugate base of the weak acid provides to the solution. It's statistically unimportant compared to this.
But if we were to have 0 for OH, then we'd use that.
Yeah.
Okay.
So now, for this, you are able to just figure out the POH. However, the POH, again, is the negative log of the hydroxide ion concentration. So you must find the concentration of the OH in excess, and that's the 50 mLs from the acid and the 52 mLs from the base. So that gives you some number that I did not write down.
I'm sorry.
What is it, 0.0?
0.0019, 0.002. This is 196.
It's a 196, so we'll call it 0.00196. Okay, pH is POH is a negative log of 0.0196. So the POH in this case is equal to, I didn't do math again. And so the pH should be 14 minus 2.7, which okay. And we're done with just a calculation for a weak acid and a strong base. And look, it took us an entire weekend to do it. All right, let's move on in the notes.